Hello, it's Keith here, and this is lesson 5 of the ARM assembly programming tutorials. We've been looking at quite a lot of commands over the last few lessons. We're on the 5th lesson, and this is going to be the final in the main series, or at least at this stage. We're going to be covering essentially all of the other major commands that the ARM2 possessed, and we're going to look at some of the later commands that are quite handy as well. This isn't the end of the ARM series though. We're going to be spreading out into platform specific series where we're going to be looking at individual platforms. We're going to be learning how to use the actual hardware on systems like RISC OS, the Game Boy Advance, and also hopefully the Nintendo DS. These systems will be looking at the hardware and we'll be doing things on those. So we've got lots more ARM content coming, but today we're going to be covering quickly the last of the commands that I think you're going to want to know about if you're programming the ARM. Okay, so let's just go straight ahead and let's make a start with today's lesson. So we're going to be working in source code as always. We're going to be using practical examples, and the first command is a very silly command called NOP. N-O-P. It does absolutely nothing. Well, why would you want this? Well, on the ARM you possibly wouldn't, but it's a command I wanted to tell you about because it's very important on systems like the Z80, maybe the 68000, systems that use self-modifying code, use it sometimes to turn off parts of the code. So it exists, but I just wanted to tell you about it. You may never need it, but if you see it, now you know what it does. It does literally nothing. So that's the first rather silly command we're going to cover. More importantly, we're going to be looking at logical operations. Now, these are things like AND, XOR, NOT. You might be familiar with these on other systems if you've done assembly before, or if you've done sort of programming or maybe some circuit design and things. I know this kind of thing comes up. We're going to go over them briefly and we will see them in a practical example. So let's just fire up today's example. So here we go. Here's our emulator. Well, what do these commands do? Well, what they do is they take two parameters and the bits will have a logical operation performed on them. And we've got various examples here. So if you look in each example, we're using R1 as our source parameter, R2 as a bit mask as it were, and then our logical operation is being performed and the result is being stored in R0. And what the AND command will do is it will say if the bit in parameter 1 is 1 and the bit in parameter 2 is 1, then the resulting bit will be 1, otherwise it will be 0. Now, if you look at our parameters, we've got 1, 2, 3, 4, 5, 6, 7, 8 in R1, and we've got 4 zeros here and then 4 Fs here, and an F is of course 4 1 bits. And so what this is effectively saying is that if the bits are 1 in this part and 1 in this part, then they will be passed through, otherwise they will be set to 0. And so the result has been that the top 2 bytes here have been set to 0, the bottom 2 bytes have been left unchanged. And I can just confirm that to you if I just change my bit mask here. If I change this to a 0, well, you can see now that this bit has been reset to 0. Well, of course, this is not being done while this is being done at the sort of nibble, the 4-bit level. This is actually, the operation is actually occurring at the bit level. So if I change the mask to FFF8 here, you can see that the 8 has been retained here. But if I change it to a 7, which is effectively a 0 and then 3 1s, well, you can see, that bottom nibble has been now changed to 0 here. So as I say, the operation is working at the bit level, and hopefully you understand enough about binary to know what these bytes might look like as binary, and if not, please use the Windows calculator or something to convert them so you can see. But as I say, although we're representing these as a 32-bit number here in hexadecimal, this is a bit level operation, and so AND is returning a 1 where the bits in both of the two parameters are 1, otherwise it's returning a 0. Now, beyond the AND command, I'll just reset this back to the starting point. Now I've explained this is working at the bit level. Now the OR command is saying that if parameter 1 or parameter 2 is a 1, then it will return a 1, otherwise a 0. And so that has the effect of setting any bit that's a 1 in either parameter to a 1 here. And so you can see that it's effectively set these bottom 4 nibbles here to F, because these 4 nibbles were F here. The bits that were 0 here, the nibbles, or the nibbles as it were, then these will be left unchanged. So kind of AND is saying, well, set to 0 anything that's 0 here. This is effectively saying set to 1 anything that's 1 here at the bit level. Now we've also got a command called EOR. This is also known as XOR on some systems, and this is inverting the bits. So where the bits are 1 in our parameter here, these are being converted, and when they're 0, they're being left unchanged. So you can see 1, 2, 3, 4 has been passed through as 1, 2, 3, 4 here, but these bits have been flipped around. So 5, 6, 7, 8 has become A987. And if you looked at the bit level, you would see that where a 1 was passed in and the parameter here was 1, it will be converted to a 0. When a 0 was passed in, it will be converted to a 1. So that's an XOR or an EOR operation, as it's called on this system. Now, that would be the limit on most of the systems I've looked at in the past for the commands that would be offered. But the ARM actually has another one called bit clear. And this is effectively the opposite of an AND command. An AND command will clear a bit where the passed parameter is a 0 here, but the bit clear will set the result to 0 when the passed parameter is a 1. So you can see that these Fs have cleared these bits here, but these zeros have left these ones unchanged, effectively the opposite of the AND command. So that's quite a handy command that may help you out in some cases. Okay, so that's a brief introduction to the logical operations that we have here, and you will need these quite a lot. You'll need your sort of AND command to mask out a certain set of bytes. Maybe if you've got a word that you've read in from somewhere and you only need a couple of bits or something. You know, maybe it's a value of a joystick and you only want the fire buttons or something. You will often need to do this kind of thing. You'll also maybe want to OR in different parts of data if you're building up a 32-bit value to write to the screen. You know, maybe you're building up a font or something, you might want to OR in the different parts as you read them in. So as I say, it's something you definitely need from time to time. Okay, so that's the logical operations. Next we're going to look at the test commands. Now, what do the test commands do? Well, the AND command we looked at just a moment ago will actually, of course, set the flags as well as performing a masking operation. And there may be times where we want to have that result of the masking operation without actually changing any of our registers. Maybe we want to see if a certain combination of bits are all 0, you know, as again if we've read in from some hardware, but we actually need that value again later on, so we don't want to have to reread it in from the hardware. Well, we can use this TST command here. Well, let's fire this up and let's have a look. Well, what we've done here is we've loaded R0 with a value here, and we've loaded R1 with the same value here. And then we've used the TST command, which is the equivalent in the term of setting the flags of an AND command. And so what this is doing is it's saying if this bit and this bit are 1, then return a 1. And then what we've done here is we've done a branch on 0. Now, because these two parameters are the same, the result is not 0, so we've shown a not equals here. So that's what's happened there. Now, of course, if we changed the second mask so that the result was 0, if we just change this here and we use this mask, now, of course, ANDing these two together will result in a 0. And you can see that's happened here. But as I say, these test commands, while it's setting the flags, it's not actually changing the registers here. So our registers are intact, even though the flags have been set as if an AND operation has occurred. Now, as well as an AND operation, there may be cases where we want to actually do the test to see if the two values are equal. And this is effectively sort of the same as doing an XOR command. Now, if we just look at this one, if we use these two parameters together, well, XORing this value here and this would result in a 0, and this is effectively saying is parameter R0 and R1 equal, because that's what the XOR would effectively do with regards to setting the 0 flag. And you can see here that's exactly what's happened. R0 and R1 are unchanged, but this time the branch has occurred because the two values are equal. So that's just a couple of rather strange commands that the ARM offers. I say strange because they're not things that I would have expected coming from the 8-bit processors and the 68000, but yeah, definitely worth you knowing about. You know, you may have a good reason to want those. Now, something the 6502 users will be very familiar with is using the carry flag to work with 16 bits, and of course other systems as well. Now, of course, our processor is 32 bits, so the carry flag for working with 16 bits is pretty irrelevant, or at least it's likely to be, but there may be cases. What, of course, this does allow us to do is actually work in 64 bits if we so wish. The actual procedure is basically the same as on an 8-bit processor, if you're familiar with them. If you're not, don't worry, we will cover it. But what we effectively do is we do a mathematical operation like an add or a subtract, and we have to update the flags by adding an S here. So we are just updating the flags as we do addition, and that will update the carry if there's any overflow to the first register. And what we can then do is we can add that carry to a second register with an ADC command, and that will allow us to work with a pair of registers, expanding the capability of those registers. So in this case, we're working in 64 bits, but of course you could work with more registers up to any value you wanted, like 128 bits or even more if you wished. So that you can see we're doing that exactly here. So we've started with a simple test value here. We're repeatedly adding R2 to R1 here, and we're adding any carry to R0. So you can see R1 here, R2 is the amount we're adding, and R0 is the effective high byte of our 64-bit pair, if you will. And so we're repeatedly adding here, and then when this low register overflows, the carry is being added to the high register because of this ADC here. And then we're doing the opposite. We're doing a subtraction and an SBC, subtract with carry here. You can see we're subtracting 0 because we don't actually want to add anything else. We just want to effectively add the carry here. And we're just looping around, and you can see here that when R1 overflows here, the carry is passed into R0, and then when R1 goes below 0, the borrow, which is effectively what the carry is subtracted from R0 here, and it carries on just fine. Now, of course, if we change our parameter here, if we change the value to add to 2 here, we just run again, you can see, of course, it just all works exactly the same. It just the carry occurs earlier and the borrow occurs later. So that's the way we can use the carry for our mathematics if we want to exceed the value of a single register. Now, of course, we do have to update the flags, otherwise things aren't going to work just right. So you saw me there, I've just taken out the ADS and the SBS, and now you can see that the carry it seems was actually set this whole time, and then it's actually been clear this whole time. So our software's malfunctioned there, because we do need to make sure we add that S to the end of our add and subtract command to update the flags accordingly. Otherwise the ADC will be adding whatever the state of the carry is. So just something to be aware of there. On most systems that would be kind of implied, but in this, on the ARM, things are a little bit different, so that doesn't happen. Okay, so on to multiplication. Now, the 68,000 users will of course be used to multiplication. The Z80 users won't be, but the ARM does have a multiply command, and you can see it just here. If we just pop that onto the top here, and the operation is very simple. We're working in 32 bits, of course, so all we're doing here is we are specifying 2 parameters to multiply here, and we can use the MUL command, and this will effectively multiply this parameter by this parameter and store it in this one here, and you can see that's what's happened here. You can see here we've got 2 times 3, and that equals, of course, 6. R3 is in this first case unused. The reason we've set R3 is we do have another command which actually, if I just move this out of the way, actually multiplies the first 2 parameters together, and that adds a third, and you can see there's some brackets there just to make it clear, and that has indeed happened there. We'll just confirm that's really happening if I just change these values here to 20 and 30, and we'll change it up to 11 just because why not, and we'll just confirm that really the multiplication is happening. And you can see here that the result is now much higher, and it has indeed gone up according to those parameters there. So as I say, this is a multiply command that we can use to do our work very quickly. Now you're probably thinking, well, that's great, now where's my divide command? Well, I'm afraid the ARM doesn't have one, which very strange. You know, coming from the Z80, I'm used to not having a multiply command and not having a divide command. Coming from the 68,000, I'm used to having both. The ARM seems to give us with one hand and take away with the other. So we've got our multiply command, but if you want to do a divide command, you're going to have to do some trickery. I believe there's a way of using the multiply to simulate a division. It's not something I'm going to cover here. Alternatively, you've always got the possibility of using loops and subtraction and seeing at what point you end up with borrow or the bit shifting operations I'm about to cover in my Z80 series that do allow it. But at this basic stage, I'd just suggest you repeatedly subtract until you go below 0, and that will be how then you'll be able to work out how many times you were able to successfully subtract by using a loop counter. But as I say, don't look for your divide command. It's not there, at least in these basic ARM commands. I'm not sure if it was added later in the more advanced ones. We're only covering ARM2 in this series. Okay, so that's our multiply command. Let's have a look at some rather strange negative commands. Now, of course, we've looked at subtraction before, but we do have these rather odd reverse subtraction commands. Reverse subtract actually reverses the order that the parameters are used. So in this case, we're actually subtracting R2 from R1, even though the parameters are kind of the opposite way round to the normal one. And we have also a reverse subtract carry RSC here. And so we can use these in the exact same way as before. So you can see here that we are subtracting 8,000 here, and we're going down each time. And this, as I say, it's basically almost the same command as the subtract commands, but it is reversed in the way that it works here. Now, as well as the reverse subtract commands, we also have a move negative command, and what this will do is it will effectively convert the parameter to a negative number and store that in the destination. So in this case, R0 will be converted to a negative and stored in R1 here, and you can see that that has happened just here. Now, as well as that, we have a compare negative, and this will effectively compare the value in a register to the negated version of the parameter. So in this case, we've loaded R2 with 5,000, and we're comparing negative, which is effectively comparing R1, which is now a negative number because of this move negative here, to the negative of R2, so negative 5,000. Now, R minus 1, 2, 3, 4 is greater than minus 5,000. So you can see we've actually shown a greater than symbol here because of our branch here. But if we did a regular comparison, of course it would be lower. So if I just do that, you can now see that we've got a less than symbol. So as I say, these commands can be used in some cases if you need to do mathematical operations and you need to flip values around or do comparisons without having to do extra stages of subtraction or converting values to negative potentially. As I say, these aren't really commands I've particularly needed, but I thought they were quite impressive commands that the ARM does offer to us, and as I wanted to cover them at this stage. Now, we've left something quite important to the end here. Generally speaking, these tutorials are ARM2 tutorials, and they did add some commands that weren't supported in the original ARM2, but they are very important commands, and these are the half-word commands. These are 16-bit commands. Of course, the ARM is a 32-bit processor. Most of the commands work at 32 bits. There's the byte commands where we put a B at the end of a command, and that will work at the byte level, but there are cases where we want to work at the 16-bit level, and with the Game Boy Advance, this is quite important for the screen and things, so we are going to cover it now. Now, all we need to do is add a H for half word. A word is 32 bits on the ARM. I try and avoid the term because I'm so used to it being 16 bits on other systems, the words, but a word is actually 32 bits on the ARM, so a half word is 16 bits. Now, let's fire this example up, and we have to run it on the Game Boy Advance in this case. And let's have a look what's actually happened here. Well, what have we done? Well, first of all, we've loaded a test value into our user RAM just here, and we've shown that to the screen here. So you can see FA, FC, FD, FE, and that's of course the little endian of this value here. Then what we've done is we've loaded in a half word from the user RAM into R0 here. And if you look at R0 here, you can see FAFC has been loaded into R0 just here, and that's the 16 bits from here, the half word from here. The top 2 bytes are 0 because we've only loaded in a half word there. Okay, and then what we've done is we've used RSB here to negate that value, and then we've stored it back just here. And so you can see here that now R0 equals 0306, and the top bits have all changed to FFFF because of that RSB command. And then when we store it back, you can see only these 2 bytes have changed here because we've stored the half word with this command just here. And as I say, load half word and store half word are basically very simple commands. They just work at 16 bits in the same way as the byte commands worked. The only reason they're being mentioned this late is because they're no use on the ARM2. So as I say, I thought best to cover them, but best to leave them later on because I don't want you trying to work on an ARM2 machine like the RISC OS we're tending to use and wonder why these commands don't work. But they are definitely worth knowing about because they're so good commands. Now, as well as these half-word commands, there is a fascinating command that the ARM does offer, and this is the swap command. Now, this swap command doesn't swap 2 registers around. What it actually does is it swaps the value of a register and a memory address here. So what we're actually doing here is we are loading in from the address in R2 here into the register R0, and at the same time we're storing R1 back into R2. So R2, R1 and R0 are all being swapped around. Well, let's see that here. Well, at this point you can see here that we've still got some values in our memory here, 06, 03, FD, FE here. And so what we've done is we've loaded R1 with 11223344 here. And then what we've done is we've swapped around R0, R1 and the memory here. And so what has actually happened is that the memory here has now taken the value R1 and R0 has taken the value that that memory had before, which is FE, FD, 0306 here. And so these two registers and this memory address have all been swapped around here. And this is going to be quite handy in some cases. Now, in this time, we used two registers, but there's no reason that we have to. It's just trying to show the full potential of the command. If we just want to swap a memory address and a single register, we can do that as well, as we've done in this case here. So this time, we've just swapped this memory address with R0 here. So R0 now contains the value the memory address used to contain, and the memory now contains the value R0 used to contain. And there we go. And there we go. So that's about all we're going to be covering on the ARM instruction set at this point. Now, there may well be more lessons coming later on, just depending on how popular this series is. But as I say, even though this is the end of the ARM processors instruction set, we're still going to be learning more about the ARM in the sense of we're going to be actually looking at hardware now from now on. So we're going to be moving over to looking at the Game Boy Advance and RISC OS itself, and we're going to be learning how to actually program the screen and do bits of input and things. So if you want to see more ARM, of course, please continue following, like and subscribe, all that kind of thing, because that really helps YouTube increase the ranking of my videos so other people can find them. I've also got a forum if you want to chat about retro programming and things, so please take a look at that. Anyway, whatever you do, I hope you enjoy yourself, hope you enjoy programming the ARM. Thanks for watching today, and goodbye.